Hi, thank you for tuning in to this Balcones train demo. I am Brandon Blaze, the founder of Blaze Capital Management. Balcones Train enables users to train neural networks using arbitrarily large datasets on their local machine, while streamlining the process from data preparation to model evaluation, and enforcing documentation and best practices to ensure reproducibility for production-ready models. In this demo, I will share my use case, work through a dummy project to demonstrate functions, and discuss the potential for project development. I am a neural network training practitioner who has built models for generating trade signals for my quant hedge fund. I ran into a problem where I was working with larger and larger data sets, which could no longer fit in the RAM of the machines I was using. I needed functions which would chunk the data and have it prepared for fast model training. In addition, I had worked on model training frameworks or pipelines, which I had kind of scrapped together, and I wanted a streamlined and standardized way of training in such a way where I could focus on the custom aspects of the iteration I was working on and less so on the routine functions. I also wanted to address any potential issues related to reproducibility with a framework that would enforce best practices, which led to this Balcones Train project. So as it stands, it currently supports a process which works on generating trade signals with neural networks that focus on categorical projects. Uh, so that's the dummy project we're going to walk through today. This demonstration will focus less so on the technical aspects of the project and more so on the functions. So we'll jump in as an overview of the project directory. We have our data folder, which stores SQL databases, and then folders related to each step in the model training process. So the process begins with data preparation, and in each of these folders, we have a script which handles the Balcones train modules and a config.py file which contains the arguments for the Balcones train modules in a centralized spot, and then custom scripts for the pieces that we want to tailor for our iteration. So in data preparation, that includes functions for creating our features and targets. So this results in a database containing our features and targets, which is a prerequisite for training, which includes a script for interfacing with the Balcones train modules. Here we will inspect our data, clean it, prepare the data in tfrecord files, and then move on to training our models. We have custom scripts for cleaning the data and any feature or target engineering we want to do at this stage, and then a script for specifying our model architecture, custom losses, and model training callbacks, our config.py, and then subdirectories for storing data and results related to model training, and then our evaluation directory, which lets us run predictions and display metrics so we can decide if a model is production ready. We have custom scripts for our business use case. In this case, we'll visualize our running profits based on model predictions, our config.py, and a directory for storing the predictions. So we'll jump in to the project. We need a raw data set. So this script creates a dummy data set. Here we'll just be working with open, high, low, close data. which we'll use for creating time series based features, technical indicator features, and it will also aid in calculating targets. So we'll run that. It creates a SQLite database. We'll go ahead and inspect that. Looks good. And here is the script which will run to create features and targets and store them in a new SQL database. Before we run this, we need to customize our feature and target engineering scripts. So we have a features function which orchestrates our specific feature creating functions up here. So this will create our standardized open, high, low closes for a 12 period window for 5 assets. That will go in one table, and we have technical indicator functions and features. So this function returns a data frame, and we have here our storage map, which specifies table names for our databases and the related column headers. So we'll have 2 tables and their columns. We'll do something similar for targets. We have our target creating function, which creates targets and data related to how long these trades will be open, and then a storage map for specifying the table name and related headers. Our config.py has arguments for how data is loaded. Throughout the pipeline in Balcones train, we will load data in batches to make sure we don't exceed the memory and RAM. And then we have arguments for creating and storing features. So that's all configured. So we'll run this and create our feature and target database. So our features are created, targets are being calculated, and we'll inspect that. So we have the 3 tables that we specified in our custom scripts. You can see that targets are not encoded yet. Here's our time series table. So these are open, high, low closes, which will reshape for time series layers like LSTM, and then our technical indicators. Now that that's complete, we'll move on to working through the training modules, which includes steps for cleaning, preparing data in tfrecord files, and then training the modules or the models. So we're going to begin by cleaning the data. First, we'll want to inspect it. Changing these bool variables indicates which modules we want to run. So we're going to begin by inspecting. We can describe and plot our tables. So we're going to begin by describing our tech features and plotting histograms of their distributions. So here we have our variable names, or our feature names, and then standard statistics. This can help with visualizing outliers and distributions. The plots are from -4 standard deviations to +4 standard deviations from the mean. So now I'll demonstrate other other ways of visualizing data. So here we're looking at the time series exchange rates, one row at a time. This can help us look for missing data or irregularities. So we have a few different ways of visualizing the data, and we can do this for features and targets. Now we'll move on to cleaning the data. So we've inspected it, and if we found something that we need to clean up, we can go to our custom script and filter for features which meet specified criteria. Um, our data is pretty clean since it was uh, generated with our custom script, but when you're dealing with real world data, oftentimes you'll need to clean it. So with these functions, we could filter for outliers, and what we're doing is collecting the primary keys of bad data, so we can then clean it and produce a clean database. So in this case, we're just looking for rows with non-values in our filter or our hourly feature table. And for targets, we're going to filter out observations that contain the target weight, which means there was not enough data available to calculate a proper outcome. So we're going to do that. You can see that it loads data in chunks, and the load data functions first figure out how big your data size is, and we'll determine the number of chunks based on that uh, to make sure that you're always able to fit these chunks in RAM. So we're going to look at the primary keys. It does it for both features and targets in this case. So now that we have that, we can go ahead and make our clean database using the align function. So it reads our feature and target database in chunks and filters filters out the bad rows based on the primary key matches and adds it to our clean database. So it just adds a suffix underscore clean to separate our data. We can see that that was just updated. And we'll look to make sure it has the same number of rows, 4856, 4856, 4856. And we can see we no longer have any non-rows. And no rows and targets that have the value weight. So that ran successfully. And now that we have a clean database, we can go on to the data preparation step. In case you want to modify or add new features at this point, you can use the engineer function. So in our custom script, we're going to add hour of day encodings and one hot encode hour pair columns. And for target engineering, we are going to encode the targets from strings to integers. And we're also going to change any buy or sell signals that take greater than 12 hours to close. And we're going to encode those into loss targets. That way we train our model to learn signals or yeah, conditions which lead to a quick turnover. So we're going to do that. and inspect our clean database. Targets are now encoded, and we can see that we correctly converted signals from buy or sell into loss where they took more than 12 hours. I know this would have been a buy signal because we have none in the buy stop loss time, but instead of being a 1, it's a 0, which means our function ran successfully. We now have our engineered feature data table, which includes the hour of day encoding and then the watt 1 hot encoding. And each of these tables still has the same number of rows. So keeping that in line is important for model training. Great. It's important to scale your data. So we have a scaling function, which will fit the scalars only on the training data and save the scalars in pickle files so we can load it during the prep and save process. Scaling your data, make sure that calculations in the model training process run correctly and training works successfully. So we're going to we we want to scale different parts of our we want to scale our feature data. So we're going to begin um, by scaling the time series data. That ran successfully and saved the pickle file. And now we want to scale our engineered features. So that ran successfully. Ideally, we just add all of the tables in a list. Currently, there's a bug which needs fixing for that. But in the meantime, we can run them one at a time. And we'll make sure that ran successfully. These were just updated and they're pickle files of the scalars. And we will move on to prepping the data and saving it as a TF record. So here we need to specify where our data is, each table, if we're applying scalars, if we want to keep primary keys. And here's our target reference. We will not scale it, but we want to keep primary keys, which will help with evaluation. So we will run that. And some notes here, it automatically saves a weights dictionary for each of our categorical targets. This helps when we have imbalanced data sets, as we do with this run. And we will inspect the prep data. We have JSON files, which save the feature name and its data type, which will help with loading these TF record files. And you can see that each file has a batch number, so we can align them when we train. And then a split, information about the split. So we have train, val, and test. This automatically splits your data so that 60% of it is train, 20% is validation, and 20% is test. And we can inspect those TF records using validate record. So we can see which file we're looking at, the feature column, its data type, and value to see if anything unexpected happened. After a quick glance, everything looks correct. So now we can begin training our model. And before we begin, we need to update a custom module script, include a create model function. Here we're concatenating the three feature sets, applying different types of layers to each. So our time series one will use LSTM layers, while the others will use dense. We'll concatenate them, run a few more dense layers, and output sparse categorical um, outputs. Here we also have a class for creating our callbacks. In this case, we'll use early stopping, learning rate reduction, checkpointing, logging losses after each epoch, and it also creates TensorBoard. We can also create a custom loss function here. And when you're training, we update our arguments here. So we need to do things like reshape certain parts of our data. We need to specify what our feature data is by referencing the prefix of the tfrecord file names, our model arguments, information for functions like model.compile, what optimizers we want to use, how many epochs, batch size, etc. And then we also save our config file, this script, and our model, custom model module script into our output directory. That way we'll have our model weights, the config and model architectures used for that iteration. That way we can replicate it for evaluation and production. So I'll begin training the model. We can see the model summary, that it correctly saved dependencies, created the directory, loaded class weights. So it's running through that. It's loading our TF records in batches. So it's training on the 60% of our data, validating on the 20%, and then we're holding out the test set for evaluation. We have a record of our callbacks, and it early stopped after 16 epochs. So we'll inspect the iteration here. It currently logs CSV of the outputs after each epoch. Sometimes you'll want to inspect it during training without stopping the training so you can see if everything's running correctly. And if you need to stop it early to make adjustments. Ideally, this will be built into the TensorBoard so we can avoid taking up more space in disk. But we can see our config and model function scripts are saved here. Let's load that quick. Yeah, our create model function, which we can reference later when we need to load these model weights. These are .h5 files. Okay, so we've trained our model, and now we want to evaluate it. We would begin by running predictions and storing the predictions in a database. I'll skip that because I would have to reconfigure our config file. So I'll reference a previous iteration. And we're going to begin by running Lime with our explain module. So we can specify from which file and what sample number we want to look at. It currently runs Lime on one observation at a time. And it shows you that it ran or it loaded the model, and we're going to run line on this specific prediction, and it prints and plots the results of feature importance. So this can be useful for understanding how your model works. Neural networks are a black box, and this can point you and can direct you for future iterations if you want to make more meaningful features. And then we'll move on to the report metrics module. And this reports standard model metrics like accuracy, precision, etc., but for different groups. So we can get metrics for our entire data set and then break it down by split. So we have train, val, and test. And these reference the same tfrecord files that the model was trained on. So it also breaks it down by pair or asset in this case, and further by asset and category. We can see it was very accurate for the majority class. In this case, it was consistent between the buy and sell signals. And we can observe irregularities or unexpected results. Like it for this pair, it was much better at predicting buy signals than it was sell. So that's interesting. In this case, it didn't predict sell signals at all for Euro USD. So that's also interesting. Even in the train set, it never predicted a sell. So you can compare data across splits, which can be useful for finding irregularities like that or observing overfitting between train validation and test splits. We have a calibration reporting module. So in this module, we are sorting our data by prediction confidence, and then we're binning it so we can find the binned accuracy. So we can plot the accuracy for bins against the benchmark. Our benchmark here is y equals x, or accuracy equals prediction confidence. And this is useful for understanding if our model confidence is reliable. Ideally, we would see a slope in our model calibration be similar to benchmark, which I think is a clear indication that it is learning meaningful signals. So in train, we do see a positive slope, and it breaks it down in the same way as our report metrics does. So we have our overall, our train asset, and furthermore by train asset and target. So something we'll see is the model is much more accurate at predicting the majority class, which contributes to the slope we see, and not very calibrated for the minority classes, which is something we'll want to improve. So in this case, we would go back and reiterate. And finally, we have our candidate filter, our report candidates. So right now it's specific to the use case of identifying models which have a high accuracy on minority classes for buy and sell signals, in other words. So it filters our prediction data set by minority classes, sorts them by prediction confidence, and creates a rolling accuracy column. And it looks through it groups that data set by asset and loops through it to see if there are any instances where the rolling accuracy from the most accurate is above our break-even level, and if it has enough samples, so we can adjust that, and we will run it, and it will print the assets that met that criteria. So for Euro USD, if the when the predictions have a confidence threshold greater than that, we have a win rate of that for this number of samples. So this will inform the custom business impact function. In this case, it's calculate running profit, which we see here. I did not filter it by these two, and instead, any instance where the confidence is greater than 0.45, we would assume we would have taken that trade, and this is what the outcome would have been, which is clearly unsuccessful. So we can customize that and visualize um, if our model is production ready. So that sums up the functions of Balcones train as it stands. Looking forward, I would like to see Balcones train expand on its core value proposition of enabling users to train neural networks on their local machine. I think it will specialize in um, providing the service for small to medium-sized data sets. Currently, I'm doing this on my machine with data sets in the dozens of gigabytes of size. So that batching feature is very valuable for me. It also streamlines the process, which addresses the reproducibility crisis in research these days, where best practices aren't followed and documentation isn't enforced, which impacts reproducibility, which would be detrimental, especially if you're using these models for production purposes. I think with this streamlined model training pipeline, it could be applicable to different use cases. Hopefully, it can be developed to handle regression tasks and also move on to things like computer vision and language modeling, for instance. And by streamlining the process, hopefully, it could even include functionality to automatically train and iterate itself by looping the pipeline and including additional functionality for machine evaluation and hyperparameter tuning. So yeah, um, I think this framework is useful, and I hope that you think so too. And if you would like to use it, I encourage you to do so. And if you find more use cases for it, I would be happy to collaborate and improve the library. So thank you for watching.